Welcome to Chapter 10, Classes and OOP. By the end of this chapter, you'll understand object-oriented programming, including encapsulation, inheritance, and polymorphism. Define and create classes and objects with their attributes and methods. Use public and private access specifiers to control data security. Develop instance and static methods. And organize classes effectively following logical guidelines. A class is a blueprint for creating objects, bundling data and behavior into one entity. A library uses a book blueprint defining what every book needs: title, author, genre, availability status. Each specific book, like To Kill a Mockingbird or 1984, is an object created from that blueprint. Books can perform actions or methods, like being borrowed, returned, or viewed. This system is exactly what lets a library organize and manage its whole collection efficiently. Here's the same blueprint idea with cars. A rental service uses a car blueprint defining make, model, year, and rental status. Each individual car, like a Toyota Corolla 2020, is an object built from that blueprint. Cars can be rented, returned, or inspected, methods that let the rental service track and manage its entire fleet effectively. And here's the same concept with trees. A botanical garden uses a tree class defining species, height, age, leaf type, and status. Each specific tree, like an oak tree 50 feet tall, is an object created from that class. Trees can grow, shed leaves, provide shade, or photosynthesize, methods that help the garden catalog and care for its collection while educating visitors. Good class design follows a few conventions. Name classes in Pascal case, clearly representing their purpose: person, car. Keep attributes private to enforce encapsulation, with clear, concise names. Provide public methods, like getters and setters, for controlled access to those private attributes. Include a constructor to initialize everything, with sensible defaults where it makes sense. And comment your code so its purpose stays clear and readable. Here's a person class as actual Java code. Private name and age attributes, a constructor to initialize them, a getter and setter for name, and a display info method to print the details. The main class creates a person object, displays its info, changes the name with the setter, and displays it again, showing encapsulation and controlled access working together. Here's that same person class in C++. Private name and age, a constructor initializing both, public getter and setter methods, and a display info method, identical structure and behavior to the Java version, just using C++'s private and public access specifier syntax. And here's the same person class in Python. Attributes prefixed with double underscores for strong encapsulation, an __init__ constructor, get_name and set_name methods, and a display_info method. Same logic as Java and C++, just Python's own naming conventions for privacy and construction. Here's a simpler person class in C++ and Java without private attributes, just public name and age, a constructor, and a display info method. This version skips encapsulation entirely, showing the bare minimum a class needs: attributes, a constructor, and at least one method before we build controlled access back in. And here's that same simplified person class in Python. Public attributes, a constructor, and a display method, the most basic possible class structure, with none of the private attribute protection we'll add back once encapsulation comes into focus. Instance methods operate on a specific object's data, using this or self to reference that object's own attributes. They require an actual object instance to call, like object.displayInfo, and they're used whenever behavior depends on an object's particular state, like updating one specific bank account's balance. Static methods instead handle general tasks that don't depend on any instance's data at all. Called through the class name itself, they're ideal for utility functions like mathematical calculations or logging that don't need any particular object to run. Here's instance versus static methods as actual Java code. Static method is called directly through the class name example.staticMethod, with no object needed at all. Instance method, by contrast, requires creating an object first, obj instance method, since it's tied to that specific object's state rather than being shared, class-level functionality. Here's that same instance versus static distinction in C++. Static method is called through the class name using the scope resolution operator, example static method, while instance method needs an actual object created first, identical logic to the Java version, just different syntax for reaching the static method. And here's the same distinction in Python. Static underscore method is marked with the @static method decorator and called directly through the class name example.static underscore method, while instance underscore method needs an actual object instance to call obj instance underscore method. Same underlying concept as Java and C++, just Python's own decorator syntax marking it as static. Object-oriented programming rests on 4 core principles. Encapsulation combines data and methods into one class, controlling access through modifiers like private and public. Inheritance lets a class derive attributes and methods from another class. Polymorphism lets a single interface represent different underlying behaviors, often through method overriding. And abstraction hides implementation details, exposing only the essential features a user actually needs. Encapsulation bundles data and methods into a single unit, restricting direct access to some of an object's components for controlled interaction. That gives you data security, preventing unauthorized or unintended changes, code maintainability, since you can update internals without breaking external code that depends on it, and abstraction, hiding complex details while exposing only what's essential. It's achieved by making attributes private and providing public getter and setter methods that only allow valid operations on that data. Encapsulation shows up everywhere in practice. A bank account class keeps its balance attribute private, with deposits and withdrawals controlled entirely through methods. A car class hides its internal engine operations, letting the driver interact only through methods like start or accelerate. And a login system stores user credentials privately, accessible only through authentication methods, never directly. Here's encapsulation as actual C++ code. Name and age are private attributes, completely inaccessible directly from outside the class. The public getName and setName methods are the only way in or out, exactly the controlled access encapsulation is designed to enforce. Here's that same encapsulation pattern in Java, private name and age attributes, with public getName and setName methods providing the only controlled path to read or modify them, identical structure and behavior to the C++ version. And here's encapsulation in Python, attributes prefixed with double underscores for strong privacy, with get_name and set_name methods providing the only controlled access, same underlying pattern as C++ and Java, using Python's own naming convention for private data. Inheritance lets a child class inherit attributes and methods from a parent class. The parent, or superclass, holds general attributes and methods, while the child, or subclass, extends or customizes that functionality, and can even override a parent's methods to provide its own specific behavior. This model's real world is a relationships well. A car class might be the parent, with electric car and sports car as subclasses, adding their own unique features on top. Here's a concrete example. The parent class animal holds a basic name attribute and an eat method. The child class dog adds its own breed attribute and bark method on top of that. A dog object gets to use both the inherited eat method from animal and its own unique bark method, combining shared and specialized behavior in one object. Here's that animal and dog inheritance as actual Java code. Dog extends animal, automatically inheriting the name attribute and eat method while adding its own breed attribute and bark method. The output confirms a dog object can call both the inherited eat and its own bark, plus access the breed attribute that only dog defines. Here's that same animal and dog inheritance in C++. Dog inherits from animal using public inheritance syntax, gaining access to the inherited name attribute and eat method, while adding its own breed and bark. Identical behavior to the Java version, just C++'s own inheritance syntax. And here's the same inheritance pattern in Python. Dog inherits from animal using super__init__ to properly initialize the parent class's name attribute before adding its own breed attribute and bark method. Same structure as Java and C++, with Python's explicit super call handling the parent initialization. Polymorphism lets objects of different classes be treated as objects of one common parent class, so a single interface can represent multiple different behaviors. It comes in two flavors: compile-time polymorphism through method overloading, and runtime polymorphism through method overriding, where parent and child classes implement the same method differently. This makes code more reusable and extensible. New classes can integrate without touching existing code, and it's key to abstraction, letting behavior change dynamically based on an object's actual type at runtime. Picture a shape drawing app. A parent shape class defines a draw method, while circle and rectangle child classes each implement draw their own way. A list of mixed shapes can call draw on every item without ever needing to know which specific shape type it's dealing with. Same idea in a payment system. A parent payment class defines process payment, while credit card payment and PayPal payment each implemented differently, letting the system process any payment type dynamically through that one shared interface. Here's polymorphism as actual Java code. Dog and cat both extend animal and override its makeSound method with their own behavior. A single animal type reference gets reassigned first to a dog, then to a cat, and calling makeSound on that same reference produces different output each time, purely based on the object's actual type at runtime. That's polymorphism in action. Here's that same polymorphism example in C++. Using virtual functions makeSound is marked virtual in the parent animal class, letting dog and cat each override it with their own behavior. An animal pointer gets reassigned between a dog and a cat object, and calling makeSound through that same pointer produces different output depending on which object it's actually pointing to. And here's polymorphism one more time in Python. Dog and cat both inherit from animal and override make_sound with their own behavior. No special virtual keyword needed, since Python resolves this dynamically by default. Calling make_sound on dog and cat objects produces different output for each, exactly matching the Java and C++ versions. Abstraction hides implementation details, showing only the essential features a user actually needs, focusing on what an object does, not how it does it. It simplifies complex systems by breaking them into smaller, manageable pieces, reducing complexity for the people using them. In OOP, it's achieved through abstract classes or interfaces, which can mix concrete, fully implemented methods with abstract, unimplemented ones. The payoff: modular design that separates interface from implementation, making systems easier to maintain and scale without disrupting users when internals change. Abstraction shows up constantly in everyday life. An ATM lets you withdraw money, check your balance, or deposit funds, all without ever seeing how it connects to the bank or processes transactions internally. A car dashboard lets you start the engine, accelerate, or check fuel levels, while the complex engine, sensors, and fuel system underneath stay completely hidden. In both cases, the interface shows exactly what you need to control, and nothing about how it actually works underneath. Here's abstraction as actual Java code. Animal is declared abstract, with an abstract makeSound method that has no implementation at all, just the what, alongside a concrete sleep method that does have an implementation, the how. The dog subclass is required to implement makeSound itself. Without that implementation, the code simply won't compile, since Java enforces that every abstract method gets a concrete implementation somewhere down the inheritance chain. Here's that same abstraction pattern in C++. MakeSound is declared as a pure virtual function, marked with =0, making animal an abstract class with no implementation for that method at all. Dog provides the required override, implementing makeSound, with its own specific behavior, identical enforcement to Java, just C++'s own pure virtual function syntax. And here's abstraction in Python. Animal inherits from ABC, and marks make_sound with the @abstract method decorator, giving it no implementation at all. Dog provides the actual implementation. Unlike Java or C++, which catch this at compile time, Python enforces it at runtime. Attempting to create an animal object directly, or a subclass missing the required implementation, raises an error the moment you try. No new assignment this time. We should be nearly done with the semester at this point, so just make sure your Canvas assignments are complete, and bring yourself to class ready to learn. It's been a long chapter covering encapsulation, inheritance, polymorphism, and abstraction, the 4 pillars that tie this whole course together.